Somewhere in our math education, we might be introduced to this formula. This 2x2 rectangular array is called a matrix, and this vertical one is called a vector, and this is the formula for multiplying them together. Now, often the only information that students are given is everything I just told you. I've introduced two seemingly arbitrary concepts, a matrix and a vector, with an arbitrarily defined operation, matrix-vector multiplication, an operation that simply needs to be memorized rather than understood. But in my opinion, this particular formula is one of the most interesting and beautiful parts of linear algebra, so I'm going to try to explain how and why this equation makes sense. Now, imagine a very large two-dimensional surface. Naturally, it has two directions that we can travel on it, left and right, and up and down. Let's also define this point in the middle to be the center or origin of the plane. Accordingly, any point that isn't the origin can be reached by traveling some amount in the left and right direction, which we will call the x-axis, and by traveling some amount in the up and down direction, which we will call the y-axis. Any point is represented with an x-coordinate and a y-coordinate then, which represents the distance along the x-axis and the distance along the y-axis that we need to travel in order to reach that point. So if I have a point that's a distance 2 along the x-axis and 3 along the y-axis from the origin, and I represent it as an ordered pair like this. But what if we're not interested in the points themselves, but the paths or arrows from the origin to these points? We'll call these arrows vectors, and say that if we have a point, for example 2, 3, then the vector from the origin to that point is written like this in purple. Notice, the vector has the same numbers as the point's coordinates. For vectors, we call these numbers components. Points and their corresponding vectors are written in almost the same way, so it might seem pointless to distinguish between them, but the difference is in what they represent. Points are simply locations on the plane, whereas vectors are paths with length and direction, so we treat them differently in calculations. And in real-life problems, vectors often represent physical trajectories and forces. Now let's consider the vector to the point 2, 3. It's reached by traveling a distance of 2 along the x-axis and 3 along the y-axis. But traveling a distance of 2 along the x-axis is the same thing as traveling a distance of 1 along the x-axis twice, and traveling 3 up on the y-axis is the same thing as traveling 1 up on the y-axis 3 times. And traveling any of those small distances individually can be represented by small vectors. Traveling a distance of 1 along the x-axis and naturally 0 along the y-axis is the same thing as taking the path described by the vector 1, 0, 1 in the x direction and 0 in the y direction. Similarly, the vector 0, 1 represents going 0 on the x-axis and 1 on the y-axis. Let's call these small vectors I and j. I is the unit vector for the x direction because it represents going 1 unit in that direction, and j is the unit vector for the y-axis because it represents going 1 unit in that direction. Naturally, any vector can then be represented as a combination of I and j. Again, the vector 2, 3 is reached by going 2 on the x-axis and 3 on the y-axis. In other words, taking the purple path described by that vector is the same thing as following 2 i's and then 3 j's. Or how about the vector -3, -1? We have two negative numbers because we're traveling backwards on the x-axis by 3 and backwards or down on the y-axis by 1. This is the same thing as taking -3 I vectors, or 3 negative backwards I vectors, and then taking 1 backwards j vector, or taking -1 j vector. Now, what if we wanted to change or transform all of the vectors in the plane in a certain way, such as making them longer or maybe rotating them? How would we describe that mathematically? Well, first, you might be wondering about the motivation for doing such a thing, so I think a good example is computer graphics. In computer graphics, the vertices of a polygon, like the triangle shown on screen, are often represented by vectors, and if we want to rotate the triangle, what we really need to do in our program is to rotate all the vectors that describe the triangle, the vectors that go to the vertices. And a rotation is an example of a transformation of vectors. Like I said before, every vector is described as a certain number of i's plus a certain number of j's, and we think of those i's and j's as steps along the plane that we follow in order to reach some endpoint which the vector points to. So if we want to transform all the vectors on the plane, say rotate them, we should just apply that rotation to I and j, and every vector will be described in terms of the new I and j, say I prime and j prime, and it will then be transformed in whatever way they were. This transformation rotates all vectors counterclockwise by 90 degrees. For example, I was originally 1, 0, that is, it pointed 1 unit in the x direction, and now it's 0, 1. When you rotate that counterclockwise, it points up, so it's 0, 1. It points up 1 unit on the y-axis. Similarly, j went from 0, 1, which is what I prime is now, to the vector -1, 0. It now points backwards along the x-axis only. So if my original vector was 2, 3, then it's transformed to the vector negative 3, 2. It's rotated counterclockwise by 90 degrees. And I'll show you how I got this result, negative 3, 2. So my original vector, 2, 3, could also be expressed as 2i plus 3j, 2 horizontal steps plus 3 vertical steps. But now that I've applied the counterclockwise transformation, I'm going to express it in terms of the transformed I and j. It's now 2i prime plus 3j prime. So it was originally 2 times 1, 0, plus 3 times 0, 1. Now it becomes 2 times I prime, 0, 1, plus 3 times j prime, negative 1, 0. 2 times the vector 0, 1 is 2 vertical steps, so the y component of my final vector should be a 2. And 3 times negative 1, 0 is 3 backward steps in the x direction, so the x component, or the horizontal component of my final vector, should be negative 3. So it's negative 3, 2. I multiply the components in these vectors by 2 and 3, and then I add the corresponding components. And it's this last part, that 2 times I prime plus 3 times j prime equals the result vector, that we're going to focus on. This is where the definition for matrix vector multiplication comes in. I have 2 times I prime, one of my new small vectors, plus 3 times j prime, the other one, and that's equal to negative 3, 2. A convenient notation that we can come up with is something called a matrix, which is this 2 by 2 array that we're defining right here, where the first column is the transformed I vector, and the second column is the transformed j vector. And so when I multiply it by the vector 2, 3, for example, I think of this matrix as representing a transformation of vectors, and I am applying that transformation to the vector 2, 3, and my result is negative 3, 2. If I multiplied this matrix or applied this transformation to a different vector, then I would get a different result. The vector was originally 2i plus 3j, but now it's 2 times whatever I becomes, plus 3 times whatever j becomes. It's 2i prime, or 2 times the first column, plus 3j prime, or 3 times the second column. And in general, this is what matrix vector multiplication looks like. X multiplies the first column, y multiplies the second column, and I add them together. Originally, the x component of this vector was how many i's were in it. But now the first column of the matrix represents the vector that I becomes. So naturally I have x of I prime, x of the new I, which is the vector AC. Similarly, y was the number of j's in my original vector, but j has become the vector BD, so my final result is going to be y times the vector BD. Here's an example of a new transformation. These are my original I and j vectors, and now they're transformed into this I prime and this j prime. So it looks like I prime has gotten twice as long and j has moved a bit to the left. It seems like by changing I, my horizontal vector, into something that's twice as long, I'm going to be dilating space horizontally by a factor of 2. I'm going to be stretching everything out horizontally so that it is twice as wide. And when I take j to j prime, it looks like the y component of j prime is the same, so the x component moves to the left. So it seems like we're shearing space. Above the x-axis, things tend to move to the left, and below the x-axis, things tend to move to the right. So I, which was 1, 0, now becomes 2, 0, and j, which was 0, 1, becomes negative 1, 1. So of course, the matrix representing this transformation takes I prime and makes that the first column, and takes j prime and makes that the second column. So the matrix 2, negative 1, 0, 1 represents this transformation, whatever it is. To get a better picture of what this transformation might look like, let's take an example vector, negative 2, 3, and see what happens to it under the transformation. Well, I take my matrix 2, negative 1, 0, 1, and I multiply the vector by it. I apply that transformation to the vector. Well, my vector was originally negative 2, 3, which means that my vector included negative 2 I vectors. But I now becomes 2, 0. So instead of having negative 2 i's, my result is going to have negative 2 I primes, negative 2 of the vector 2, 0. Similarly, my original vector had 3 j's, but now it's going to have 3 of whatever j becomes, and j becomes negative 1, 1, so we're going to add 3 of the vector negative 1, 1, and the result is 1, 3. So negative 2, 3 is mapped to 1, 3. I hope this video gave you a clearer picture of what matrix vector multiplication really is and what it means, how matrices can be thought of as transformations, and most importantly, about how we can approach math education in an intuitive and deliberate manner.